Next, let's look at a problem that involves finding the heat that's needed to accomplish a phase change. So in this example, we have a 50-gram cube of ice, which is initially at 0 degrees Celsius, so it's right at its melting point. It's dropped into 200 grams of water in an 80-gram aluminum container. Both of the water and the container are initially at 30 degrees Celsius, and we want to know what is the final equilibrium temperature of all of these materials. So we know that if we have objects in contact exchanging heat, the sum of those heat exchanges is going to be 0. In this case, we have 3 materials that we're starting out with. We have the ice, the water, and the aluminum container. So we have Q for the ice plus Q for the water plus Q for the aluminum container are going to sum to 0. So next I'll specify more what each of these Q's are. First, let's look at the ice. Q for the ice is going to be equal to, well, let's see. The ice has to do 2 things. First, the ice has to melt, and then that melted water has to come to a final equilibrium temperature with everything else. So we could write down that Q for the ice is going to be equal to the mass of the ice times the latent heat of fusion for ice, because the ice has to first melt, and then there will be an additional amount of energy that enters the ice or the ice water now to raise its temperature. So then we have to add to that the mass of the ice times the specific heat of water, because once it finishes melting it becomes water, times the final temperature, and this is the final temperature of everything since everything comes to equilibrium, minus where the ice water starts out, which is at 0 degrees Celsius. So that would be the heat exchange for the ice. Then we have the heat exchange for the water. So Q for the water is going to be equal to the mass of the water times the specific heat of water, and then times T final minus the initial temperature of the water, which was 30 degrees Celsius. Finally, we have the aluminum container, and that's going to be equal to the mass of the aluminum times C for the aluminum, and then times the final temperature of everything minus the initial temperature of the aluminum, which was 30 degrees Celsius. All right, so I can sum these 3 things and set them equal to 0, and I want to find what is that final equilibrium temperature. So if I sum all of these terms together, then I would have the mass of the ice times the latent heat of fusion plus the mass of the ice times specific heat of water, T final minus 0 degrees Celsius, then the water term plus mass of the water, specific heat of the water times T final minus 30 degrees Celsius, plus the mass of the aluminum, specific heat of the aluminum, T final minus 30 degrees Celsius, and all of that sums to 0. Okay, I know the thing I want to find is T final, which appears here, here, and here. So the next thing I'll need to do to get at that T final is multiply over the parentheses these terms that have T final in them. So if I do that, I'll get mass of the ice, latent heat of fusion, plus mass of the ice, specific heat of water, T final. And then if I multiply this times 0, well, that just gives me 0, so that term drops out, plus mass of the water, specific heat of water, T final, minus mass of the water, specific heat of the water times 30 degrees Celsius, plus mass of the aluminum, specific heat of aluminum, T final, minus mass of the aluminum, specific heat of the aluminum, times 30 degrees Celsius, and all of that sums to 0. Okay, so if I want to find T final, I'll take all of the terms that have a T final in them, leave them on the left-hand side and then move all of the terms that do not have a T final in them to the right-hand side. So if I do that, I will get mass of the ice, specific heat of water, T final, plus mass of the water, specific heat of water, T final, plus mass of the aluminum, specific heat of aluminum, T final, and that's going to be equal to, and I move this term to the other side, which gives me a minus mass of the ice, latent heat of fusion. Let's see, then there's this term plus mass of the water, specific heat of water times 30 degrees Celsius. And then finally there's this term plus mass of the aluminum, specific heat of aluminum, 30 degrees Celsius. Okay, so then I need to factor out a T final out of these three terms. So that's going to give me T final times mass of the ice, specific heat of water, plus mass of the water, specific heat of water, and then plus mass of the aluminum, specific heat of aluminum, and then that's going to be equal to all of this stuff here. So minus mass of ice, latent heat of fusion, plus mass of water, seawater, 30 degrees Celsius, plus mass aluminum, C aluminum, 30 degrees Celsius. Okay, so then the final step is to divide both sides of the equation by this term in the parentheses. So let's see, that gives me a T final equal, and I think at this point I will just start plugging in numbers. So I'll start with the stuff over here, which then becomes the things in the numerator. So minus the mass of the ice, and the mass of the ice is 50 grams, which is the same as 0.05 kilograms, times the specific heat of water, or actually times the latent heat of fusion. So the latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. I can look that up in a table, either online or in the textbook. So let's see, that's this term. And then I have to add to that plus the mass of the water, and the mass of the water is 200 grams or 0.2 kilograms, times the specific heat of the water, 4,186 joules per kilogram degrees Celsius. And then I also need to multiply that times 30 degrees Celsius, so times 30 degrees Celsius. Then I need to add to that plus the mass of the aluminum, which is 0.08 kilograms, times the specific heat of aluminum, which I can look up, and that is 900 joules per kilogram, and then times 30 degrees Celsius. Okay, so that all gets added together, and then that whole thing is divided by mass of the ice times CW. So the mass of the ice was 0.05 kilograms, and then the specific heat of water is 4,186 joules per kilogram degrees Celsius. And then I add to that the mass of the aluminum, plus the mass of the aluminum was 0.08 kilograms, and then the specific heat of the aluminum is 900 joules per kilogram degrees Celsius. And then I also add the mass of the water times CW. So the mass of the water is 0.2 kilograms, and specific heat of the water is 4,186 joules per kilogram degrees Celsius. So if I put all that into a calculator, I will find a final temperature of about 9.50 degrees Celsius. So that would be the final temperature that all of these materials reach. So It looks like there's the lot here, but it's actually just a bunch of algebra. The important stuff all happens up here, where we figure out what goes into each one of these heat exchange terms. So for ice, we had to melt the ice, and then we had to take that ice water and raise its temperature to whatever the final temperature of all three materials are. We knew that that final temperature would be warmer than the 0 degrees because everything else started out at 30 degrees Celsius. So heat is going to be flowing out of these warmer materials and into that ice and the ice water. Then we write down the heat exchange for the water and the aluminum and add them all together, set it equal to 0, and then we can solve for our unknown, which in this case was the final equilibrium temperature. So next, let's look at this question. A friend dares you to walk across a bed of hot coals. In preparation, what should you do? Stand in a bucket of water, surreptitiously put on your iron-soled shoes, rub your feet with dry ice, or throw in the towel and buy lots of Band-Aids and aloe gel.